Okay, the next concept we're going to look at is called heat loss equals heat gained. Or if you looked this up online, you might see it called Q equals Q. Some people do Q equals negative Q, but again, I like to use positives whenever possible and just think through if things are getting hotter or colder. So that's why I'm just doing Q equals Q. Heat loss, heat gained, remember that Q in our formula did mean heat or energy. So if you think about a cup of ice, or sorry, a cup of water with some ice in it, those are two different objects, the water and the ice. And why did you put that ice in your water? Probably because you wanted your water to get cooler. So when you first put the ice in the water, before any heat exchange has happened, the water is hotter comparatively, and the ice is colder. That means the heat is going to flow from the water to the ice. That water is losing heat. That's why your water ends up colder. That ice is gaining heat. That's why ultimately the ice ends up melting. And eventually, when does this heat transfer stop? When does that flow stop? When the two have reached the same temperature. If one were still hotter than the other, there would still be some heat to flow from one to the other. But whatever amount of heat one thing loses is the exact amount of heat in a perfect world that the other one is going to gain. So whether it's water and ice, or you'll see a lot of our example problems end up using a piece of metal and water, two objects at different temperatures, the heat is going to flow from the hotter object to the colder object. And so that's what we mean by heat loss, heat gained. Let me show you an example problem. So we have this example problem here. Let's read it first, and then we'll go through like we did before and underline and figure out what everything means. 20 grams of a metal at 80 degrees Celsius was added to 30 milliliters of water at 20 degrees Celsius. The temperature changed. Find the specific heat of the metal. So frankly, just from that first sentence, we have a metal at 80 degrees. And we have water at 20 degrees. Two different objects at two different temperatures. We know some heat is going to transfer, and the heat lost is going to equal the heat gained. So that's how we know this is a heat lost, heat gained problem. Make sure that makes sense, or rewind and rewatch that part. When we're looking at these problems, heat lost, heat gained, I would say organize your information like this. We're going to make a list of information about each object. So in this case, one object is the metal and the other object is the water. And if we're saying that heat lost equals heat gained, we weren't given a set amount of heat for either, but we do know from before that Q equals mCp delta T. So for this Q of, let's say, the metal, I'm going to use mCp delta T. And for this Q, let's say, of the water, I'm going to replace that with mCp delta T. And those two things are going to be equal. So it's not a new formula. Like if we were in person on a test, I wouldn't give you this formula, mCp delta T equals mCp delta T. You should be able to figure out that, okay, heat lost equals heat gained, and heat can be found by mCp delta T. So for the metal and water, what we're going to care about are the M, the Cp, and the delta T, though we're rarely actually given the change in temp like that. So instead, when we're organizing our information, I'd expect you to have an initial temperature, a final temperature, that's with the I and the F, initial and final, and then a change. And same for the water, mass, specific heat, frankly, it's water. I'm just going to plug in 4.18, initial temp, final temp, change in temp. Going through my question, 20 grams of the metal. So we have 20 grams of it. It was at 80 degrees. That means it's initially at 80. Before we combine it with the water, if it's at 80, that's its starting temperature. And it was added to 30 milliliters of water. For water, we know that milliliters is the same as grams at 20 degrees Celsius. So that's its initial temperature. The temperature changed until it reached a temperature of 30. Now, I want you to think carefully. What does this question mean when it says it reached a temperature of 30? Does it mean the metal? Does it mean the water? Hopefully, you're thinking it means both, Remember, the metal is hot. So I'm gonna pretend like there's an invisible thermometer in front of me. The metal's hot. It's high up on the thermometer scale. The water is cool. It's pretty low down. The metal's going to give its heat away to the water, right? That energy, heat energy, is going to flow from the hot thing, the metal, to the cold thing, the water. As the metal loses heat, its temperature goes down. As the water is gaining that heat, its temperature goes up. And that process continues until they reach the same final temperature. Our final temperature will always be the same, or it's not our final temperature. We didn't let all of the heat transfer. So when it says it reached a temperature of 30, that means both of them. And what that allows us to do, by having the initial and final temperatures for each, we can find the change for each. Again, just do bigger minus smaller. So 80 minus 30 would get us a change of 50 for the metal. 30 minus 20, 30 minus 20, bigger minus smaller, would get us a change of 10 for the water. They don't change temperature by the same amount. They end at the same spot. But because we have different amounts of the metal and the water, and they're different materials, metal and water, how their temperature changes differs, even though the amount of heat they transferred is the same. Again, think of like the metal fork and the plastic fork, or the two different size pots of water. Same amount of energy going to both, you're going to end up at different temperatures. Different changes in temperature, same final temperature, or else they just keep changing till they get to the same spot. That didn't make sense, pause and rewatch, come ask questions. Frankly, now that I have all this information, it's just plugging in and doing some annoying-ish algebra. Make one side the metal, one side the water, just so you stay organized. For the metal, we're looking for the CP. That's what it asked us to find the specific heat. So that'll be our X. Our mass is 20. Our CP is what we're looking for. Make sure you just plug in the change of 50. Keep things nice and simple. For water, our mass was 30, our CP is 4.18, and our change was 10. So annoying algebra, but multiply out the right-hand side. Take 20 times 50 and leave that multiplying by the X on the left. And then divide both sides by 1,000. Since this is a CP we solve for, joules per gram degree Celsius, that would be my answer. One more example for you, just to point out a couple other things or variations we could do on this type of problem. It's still a heat loss, heat gain, so I'm going to quickly organize my information like I did for you before. So we have tin in this case, and we have water. For the tin, it says our mass is 20. It says our CP is 0.21 joules per gram Kelvin. Just because it says joules per gram Kelvin, it does not mean I need to change anything to Kelvin. Again, the difference, we're using change in temperature. So the difference in 2 kelvins and the difference in their 2 equivalent Celsius values is going to be exactly, through my stylus, is going to be exactly the same. So the fact that it says Kelvin, whatever, you can pretend it's Celsius. At 30, that's an initial temp. Was added to 80 grams of water. Water, we know its CP is 4.18. They don't have to tell us that. At 90. Find the final temperature of the metal and of the water. Now, it is worded to be tricky on purpose. What you need to know, we're looking for the final temperature, so call that X. How does the final temperature of the tin compare to the final temperature of the water? Remember, the hot thing, the cold thing, hot thing is giving its heat away, cold thing is heating up, and they'll keep transferring that heat until they reach the same final temperature. So if X represents my final temperature of the tin, X also represents the final temperature of the water. Your final temperatures are the same, even though your change in temperatures never will be. If I then say, okay, great, I know where X is, let's go plug in mCp delta T equals mCp delta T, you'll realize, shoot, I need a change in temperature for this formula, and I don't have a change. The algebra on these problems is going to be more annoying, but I can tell you for change in temperature, as I've always said, do bigger minus smaller. Now, how do you know if X is bigger or smaller? This is when I'd say draw that thermometer I keep doing. I'd say draw out a thermometer. It doesn't have to be fancy. Boom, there's a thermometer. 90 would go at the top of the thermometer, and that's where water starts. 30 is obviously lower than 90 on a thermometer, and that is where the metal starts. And where are they going to meet? Somewhere in the middle. We don't know if it's closer to the 90 or closer to the 30 because it depends on the specific heat of each substance and the mass of each substance. So you can't just average the two. That will very rarely, dare I say, never work. But somewhere in between the 90 and the 30 is where they both end, or the final temperature for both. So if you can put the big temperature, the small temperature, the X will always be in the middle. They are always meeting somewhere in the middle, even if it's not halfway. So then bigger minus smaller. Remember, on a thermometer, the bigger numbers are up top. 90 and X, 90 is on top, so 90 is bigger than X, bigger minus smaller. For the metal, X and 30. X is on top of the 30, so X is bigger, bigger minus smaller. Always, 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 please never put a plus sign anywhere in the change. I don't know why people do that every year, no matter how much I emphasize this. Always bigger minus smaller. X is always going to be smaller in one instance and bigger in the other. Draw your thermometer to know. Come ask for help if that doesn't make sense. Now we can plug in. For the tin, mass 20, CP 0.21, change in temp X minus 30, that whole expression. For the water, mass is 80, CP is 4.18, change in temp is 90 minus X. Sorry, that's not showing up well, but that says 90 minus X. Okay, in terms, if the algebra is easy for you, skip ahead. What I'd tell most of you to do is multiply the numbers and leave the X minus 30, 90 minus X out of it for a second. So 20 times 0.21, I have 4.2, and I then leave the X minus 30. 80 times 4.18 gets me 334.4, and then leave the 90 minus X. Now, hopefully this is a lot less intimidating and we can distribute. So we'll do 4.2 times X and 4.2 times negative 30. That gets me 4.2X minus 4.2 times 30. Then we'll take the 334.4 times 90. That gets us a really big number. Minus 334.4 times X. Then we want to get our terms that have X on the same side and our terms that don't have X on the same side. So I'm going to add the 334.4X to this side, so it comes off of that side. And I'm going to add the 126 over here, so it comes off there. 4.2 plus 334.4, we now have 338.6X equals 30,096 plus 126. We want the X by itself, so we divide by 338.6. And we get an X value of 89.26. Oh my gosh, after all that algebra, that's annoying. What on earth does X stand for? Are we done? Do we have to do anything else? X was my final temperature of the tin. X was also my final temperature of the water. That's why we bother organizing our information. What did they want us to find? The final temperature of the tin and of the water. That is our only answer. It is the final temperature of the tin and of the water. We're not looking for the change, so we're not going to plug it in there and there. We're looking for the final temperature, and that's what X represents. Go try.